All right, so we're going to perform some similarity transformations here. Um, Much like transformations, composition and transformations like we did before, we're going to do the one on the right first. So we're going to use a scale factor of 0.5 and do a dilation based on that. So this 0.24, if you multiply each coordinate by 0.5, you get 1, 2. This point is half as far from the origin and in the same direction as A. And then we'll do that with negative 2, 8. Multiply each coordinate by 0.5, we get negative 1, 4. Same thing with point C, which is 0, 10. That will become 0, 5. So we have this new triangle where each side is half as big as it used to be because the scale factor was 0.5. I guess I'll use primes here to notate the new ones. Next, we're going to reflect it across the line M. And the line M is x equals negative 3. So we need to graph that line x equals negative 3. So it's going to be a vertical line where all the x values are negative 3. And then we're going to reflect each point across there. Each point will be the same distance from that line, but on the other side, reflecting across there. So A is 1, 2, 3, 4 units to the right. I should say A prime. So A double prime will be 4 units to the left. Still has the same y coordinate as before. B prime is 2 units to the right of this line, and so B double prime will be 2 units to the left of that line. And then C prime, which is 1, 2, 3 units to the right, will be 1, 2, 3 units to the left. So A triangle A double prime B double prime C double prime is similar to triangle ABC, and it's half as big as that. All right, this one's a little bit different. We're going to do a translation along the vector 1, negative 2. So to the right 1, down 2. And then we'll do a dilation by a factor of 2. So let's get these original points plotted. Each of these points we're going to shift to the right 1, down 2. So x prime will be right here. To the right down 1, down 2. Y prime be right here. And then z prime be right there. Now, dilation with a factor of 2 means we'll multiply each of these coordinates by 2. So 0, 2, that's an easy one to do. It'll become 0, 4. So this one in red will be the new y prime. X is currently 4, 3, so double that, each coordinate. That'll be 8, 6. And then let's see, z prime is 2, 5, so z double prime will be 4, 10. And so we'll connect those. Not the straightest of lines. And so we have our similarity transformation. This triangle x double prime and y double prime z double prime is similar to triangle x, y, z. Same shape, but not same size. The new one is twice as big because of a scale factor of 2, and it's in a new position in the coordinate plane based on that translation. All right, this time we have the original figure, we have the new figure. We're trying to figure out a composition of transformations that will take one of those to the other. Our original one is the first one mentioned in our sentence. So the triangle XYZ is the original. Now it's kind of up to you. You could try to get it in the same size and then get it in the same position, or you can kind of get it in the same position in comparison to the origin and then try to get the same size. And I think I'll take that second approach, especially based on the grid that I have provided to me. If I double everything here or make it bigger, it looks like it'll be off the grid. So let me do what appears to me to be a rotation. I want this smallest side to match up with this smallest side. So let's see, maybe 180-degree rotation about the origin. That might do it. So if you think about where x is compared to the origin and then rotate it 180 degrees, that's going to put it right there. So I guess I'll call it x prime would be at -2, -1. And you may remember the rule for rotation, 180 degrees about the origin. Your x and y coordinates change sign. So let's see, 2, 1 becomes -2, -1. Each coordinate changes sign, unless we can follow that pattern, or we can just think through the rotation for the y and for the z. So currently y is at 1, 4, so the new y will be at -1, -4. The current z is at 4, 1, so the new z will be at -4, -1. So now it appears to be in the correct position, but it needs to be the same size. So I want this 2 to become 4, this size to become 4, so I'll have to double each one. And so if it's so let's see, that was a rotation about the origin. Capital R is reflection in transformations in this textbook, so we use lowercase r, 180 degrees about the origin. This is our first transformation that I did, and then we're going to see a dilation with a factor of, it looks like 2. So let's see if this works. So -2, -1 becomes -4, -2. Yes, that's good. -4, -1 becomes -8, -2, multiplying each coordinate by 2. And then -1, -4 becomes -2, -8. And so that does work. So this is the correct, rewrite this. This is the correct composition of transformations that allow you to map one to the other. Here's your official definition. A similarity transformation is a composition of one or more rigid motions and a dilation. A similarity transformation results in an image that is similar to the pre-image. Properties that are true for any similarity transformations. The reflexive property, anything is similar to itself. Symmetric property, if A is similar to B, then B is similar to A. And then transitive property, if A is similar to B and B is similar to C, then A is similar to C. So that holds true for any similarity transformations. All right. Here, an artist is looking at a sketch that she was thinking about putting on a wall that's 15 by 20. So let's see, the 11-inch side would have to match up with the 15-foot side, and the 14-inch side would have to match up with the 20-foot side, excuse me. So that's one way you could write this potential proportion. If these are equal, then they will be similar. If the proportion is equal, then the figures would be similar. Another way that we could write this is 11 inches, the smaller side compared to the bigger side, and then the smaller side to the bigger side on the other one. What's nice about this version is then you can go ahead and divide out the units. Inches divides out, feet divide out, and so now we can just focus on the numbers. So one of the ways you can solve this is cross multiply. 20 times 11 is 220. And then 14 times 15, I believe, is 200. Or sorry, 210. So these are not equal. And so there is no way for her to take this sketch and put it on the 15 by 20 wall and have no like blank space or anything. So there is not a way to make this similar because the sides are not proportional. So she cannot copy this and put it on that wall with no blank space. All right, here it says write a proof that any two circles are similar. Now I'm not going to actually write the proof, I'm just going to kind of talk through it. If we translate this circle to this one so that the center matches up, then we'd have two concentric circles, circles with the same center, or a center at the same point. And then we could just simply multiply this one by S over R. So our scale factor, we often use K for that, would be S over R. And once we do that, then this one will map to this one. Because circles are collections of points that are equidistant from a single point called the center, all circles will be similar. They all have the same shape, just not necessarily the same size. So a simple translation, whatever it takes to get from P to Q, and then a dilation with the scale factor of S over R would map this one to this one, and then since we use the similarity transformation, then the figures are similar. So whatever translation it takes to get to Q from R, and then also a dilation with a factor of S over R. And so that would be enough to show that those are similar. All right, so similarity transformations, composition of one or more rigid motions and a dilation. And then two figures are similar if there's a similarity transformation that maps one to the other, and all circles are similar.